All right, so last class we talked about, very briefly, about the t-distribution, right? So the idea is that we have n random samples from a normal distribution, and the issue is that we don't know the variance, right? So the variance of the population is unknown, right? And that means that we estimate the variance from the samples, right? So we have S, but we don't have sigma, right? And we also don't have many samples, right? So n is like 20, is 10, right? It's not like 40 or 50. N is not a large number. So in that case, x bar minus mu divided by S divided by square root of n is a t-distribution, basically follows a t-distribution with n minus 1 degrees of freedom, right? So degree of freedom means, how many samples you have, right? So I briefly talked about it before, again in the same context, like in robotics, it's a very common concept, right? So when something is moving on a plane, we say that it has 2 degrees of freedom, right? It can move in the x and y directions, right? Or if you consider a 3D object moving in 3D, it has 6 degrees of freedom, right? It can move in 6 degrees. So in statistics, it's a quite similar concept, right? If you collect n samples, right, each one of those is sort of like a degree of freedom because each one of those can change, right? And the reason that we subtract 1 and say the degrees of freedom is n minus 1 is that we calculate the mean from the samples, right? So we add them up, we calculate the mean. So the mean is something, sort of, we can assume that the mean is set. And because of that, we lose 1 degree of freedom, right? So there is the summation of all of the numbers should be n times mean. And because of that, we lose 1 degree of freedom, right? So I mentioned that this was actually discovered by, I mentioned the story. So the person who discovered it was working in a beer factory, right? And, I guess he was trying to optimize, brewing of beers, right? So similar to, forgot actually the character's name, but the movie, the series Breaking Bad, right? Yeah. So he basically discovered this new distribution, right? And his company didn't allow anybody to publish the results, so he always published under pseudonym students, right? He has a couple of papers, one of them is this one. Right? So this is how the t-distribution looks like. It's very similar to a normal distribution. So like normal distribution is symmetric. The difference is that it has heavier tails, right? So for example, if you look at degree of freedom equal 1, so nu equal to 1, you see that basically it doesn't approach 0 as fast as Gaussian, right? So in this case, if the degrees of freedom is infinity, it becomes a Gaussian distribution, right? So the black curve in this curve is the Gaussian distribution, and you see that the Gaussian distribution approaches 0 very fast, right? It means that these numbers, for example, number 4 is very unlikely, right? But with t-distribution is not as unlikely. The probability is a little bit higher, right? So if x bar is the mean that we calculate from a few samples, and S is the standard deviation that again we calculate from a few samples. And these are basically computed, X's are sampled from a normal distribution. So the original distribution was normal, right? So the idea is that we have some normal distribution, right? And we are sampling X's from this, right? So X1, let's say X2, X3, X4, right? So let's just to be symmetric, let's make one more. So X5, right? So let's say we have made 5 samples from a normal distribution, right? And we know nothing about this normal distribution. We don't know its mean, we don't know its variance. All we know is that it was a normal distribution, right? Then the confidence interval for mu is going to follow this equation, right? So it's very, very similar to the case for for the Z distribution or normal distribution. The only difference is that here, instead of Z of alpha divided by 2, we have T of alpha divided by 2, right? So if you contrast this with the previous equation that we had, it's exactly the same. Everything is the same, so it's x bar minus something times, actually the other difference is that here we have S or sigma, right? Divided by square root of n, right? So, but the only difference is basically this guy that's replaced, that we use instead of Z, right? And since it's T, we have to use the T distribution table, right? So if you look at the formula sheet, there is also, like, this T distribution is also provided, similar to the normal distribution. So this is the two-sided confidence interval, right? If we want to know what are the upper and lower bounds of mu. But similar to the cases before, right? We might only need a lower bound, right? Or we might only need an upper bound, right? And in that case, the equations are exactly the same as before. The only difference is that if we are, for example, looking for an upper bound, instead of T of alpha divided by 2, we use, so for upper bound, we use T of alpha, right? Same here. For lower bound, instead of T of alpha divided by 2, we use T of alpha, right? So if we only want to know mu is more than something, for example, for the lower bound. So if you completely understood, the previous confidence intervals, this is not something new. It's very, very similar to previous cases, right? And all of these, in my opinion, are quite easy, right? So even if you didn't understand the previous cases, we can, understand the mechanics from the following example that we see. Any questions so far? Okay. So we want to construct a 95% confidence interval on the following data, right? So this is a very realistic case because we don't know the mean of the distribution, we don't know the variance of the distribution, we have to estimate everything from the data itself, right? The only thing we're assuming here is that the original data was normal, which is something that we almost always do, right? When we don't know anything about the problem, we can assume that, it's a normal distribution. So the first thing we have to do is that we have to count how many samples we have, right? So if we count, it's a table of 4 by 1, 2, 3, 4, 5, 6, right? So it's 6 times 4, 24, but 2 of these are missing, right? So it's 22 samples, right? So we have 22 samples. So it's very important to subtract 1. So 21 is the degrees of freedom, right? We always have to subtract 1. The reason is that that's how this distribution works, right? So the numbers that are provided here in this table, right? These are n minus 1s. These are not n, right? So the first thing you do, you subtract 1. So n minus 1 is 21. And then you have to calculate x bar, which is relatively easy. It's 13.71, right? We also have to calculate s squared, right? And we have the equation for s squared. It was sigma xi to the power 2 minus sigma xi, the whole thing to the power 2, divided by n, divided by n minus 1. Something like this. Right? So using this equation, here you have to do, a number of computations. So you get, what do you get? 3.55, right? Yeah, thank you. Thank you very much. Yes, I have to throw a chocolate for you. That's right. It's 3.55 to the power 2. And that's a very common mistake, right? This equation is s squared. So then, based on this, we calculate So the question tells us that we want 95% confidence interval. And if the question doesn't say anything, it's a two-sided confidence interval always. If it's one-sided, it will tell you like a lower bound or upper bound, right? If it doesn't say anything, it means it's a two-sided, right? So since it's two-sided, we have to calculate basically T of, so if we look at the previous slide, it's T of alpha divided by 2 and n minus 1, right? So T of alpha divided by 2 and n minus 1, right? So basically from the table, we have, So from the table, we have this number, right? So this thing keeps blocking the, so if you look at the last row of this table is n minus 1 is 21, and this column is 0.25, right? So the number that we need here is 2.80, right? So if I go back, this number here is 2.080, right? Oh, sorry, this number. And we have S, right? It was 3.55. And here we have to plug in square root of 22, right? And we also know X bar, right? So we know everything from this equation, right? So we had 22 samples. We calculated S from the data, and for T of alpha divided by 2 and n minus 1, we have to look at the table. We have to look at row n minus 1, and then alpha was 0.05. So alpha divided by 2 is 0.025. So the number is this number. And then we plug into that equation, right? And we get mu is between 12.14 and 15.28. Any questions? Yep.
How did we get alpha?
Yeah, so the question says, that's a good question. So the question says you have to calculate a 95% confidence interval, right? So if I go back to the equation, this equation is for 100 times 1 minus alpha percent confidence interval, right? So when this thing is 95, it means that alpha is 0.05, right? And that means that alpha divided by 2 is 0.025. Yeah, sorry, I should have mentioned. So this is the percentage of the confidence interval that you get. Thank you. Any other questions? Okay, so let's consider a hypothetical case where we knew that the population standard deviation is 3.55, right? So in the previous example that we did, all we knew was these 22 data points, right? We didn't know anything else, right? So assume that in addition to these, 22 data points, somehow, let's say magically, we knew that the population standard deviation is 3.55, right? So in this case, and again, we want a 95% confidence interval for the mean, right? So we want to find the 95% confidence interval for the mean of this basically distribution. So what equation should we use? Should we use the t distribution or the normal distribution in this case? Yes, exactly. We have to use the normal distribution because we use t distribution when we don't know the variance of the population, right? Here, the variance of the population is known. The question tells us that the variance of the population somehow magically is known and is 3.55, right? So in this case, I have to use z of alpha divided by 2, right? Which is z of 0.025, sorry, right? And that z is, if you solve enough questions over time, you memorize that, is this number. So in the table, so this is the normal distribution. So the previous table, if I go back, this table was for the t distribution, right? Here, since we know the population standard deviation, we have to use the normal distribution, right? And in the normal distribution, z of alpha divided by 2 is this number. Oh, sorry, this number is closest. Sorry, I made a mistake. So this number in purple. Right? So this number is closest to 0.025, right? So my mu is going to be between x bar minus 1.96 times 3.55 divided by square root of 22 and x bar plus 1.96, 3.55 divided by square root of 22, right? So that's the solution in this case. Everything is quite similar to the case for the previous slide. The only difference is that here I'm using the normal distribution to find 1.96 instead of the t distribution, right? And you see that in this case, this number, the previous slide, the number was, what was the number? 2.08, right? Here the number is 1.96. It's a smaller number, right? So it means that, here mu was between 12.14 and 15.28, right? Here it will be, like this number will be a smaller range compared to before, right? So, So in this case, we had, between 12.14 and 15.28, right? That's our confidence interval for using the t distribution when we don't know the population variance. But if we know the population variance, the range will be a little bit smaller, right? And that's intuitive because now we know additional information about the distribution, right? And because of that extra information, our confidence interval is a little bit smaller. It means that we are more certain where the actual mean is, right? And remember, the meaning of the confidence interval is the probability that the actual population mean is somewhere here, right? That's the meaning of confidence interval. Any questions? Okay. So is there any other case where, like in the original case, we had to use the t distribution, right? So in one hypothetical case that we know the population standard deviation, we have to use the normal distribution instead of the z distribution. Is there any other case that we have to use the normal distribution? There is actually one other case where we have to use the normal distribution. Does anybody remember what was that case?
When the mean is known also.
Yeah, that's a good point. Yeah, if the mean is known, actually I'm not 100% sure. I was thinking about that. I'm not 100% sure about that. I think you will have to, we don't cover that in this course, but I think that's the case. If mean is known, then I think if mean is known, then it basically doesn't follow any of the things that we mentioned. You still have to use the t distribution, but instead of n minus 1, you can use n. So I won't confuse anybody. We will not talk about that in this course, right? So we never give you a case where the mean of the population. Actually, if the mean is known, then there's no question. Okay, I'm glad you asked that question. So in this case, what would we do if the mean is known? If the mean of the population is known? We don't need to do anything, right? Because we are trying to find a 95% confidence interval for the mean. And the mean is already known, right? So there's no question, right? So for example, if the question tells us that, assume that we know that the population, mean is whatever, what was the X bar that we calculated? 13, right? In fact, we can calculate, instead of a 95% confidence interval, we can calculate a 100% confidence interval. And that confidence interval is exactly the number 13, because the question already gave us what mu is, right? So for these cases, we never know mu. We don't know, population mean. If we knew population mean, it's a silly question to ask what's the confidence interval for the population mean, right? So we never know the mean. So going back to the original question, what was the other case where we use, so in this case, we have 22 data points, and because of that, we have to use the Z distribution. Is there any case where we don't know population mean, we don't know population variance, we want to calculate a 95% confidence interval for the population mean? All we have is just a bunch of data points. Yeah? Exactly. If you have 40 samples or more, right? If you have many samples, right? Instead of 22, if you have 40 samples or 41 samples or 50 samples, then we use the normal distribution, right? And in fact, if you look at this table, right? The table for percentage points of the T distribution, if you look at the rows that correspond to large numbers, you will see that as the numbers get larger and larger, the values get closer to the normal distribution. And we can also see that from this graph, right? As the degrees of freedom get larger and larger here, the distributions become more and more similar to the normal distribution, right? So going forward, this was the second hypothetical case that we solved, but a third case would be if we had, for example, 40 data points, right? If we had 40 measurements from our data, so here we have only 22. Instead of 22, if we had 40, we can calculate X bar from the data, we can calculate S from the data, and then we can use this equation that mu is more than X bar minus Z of alpha divided by 2 S divided by square root of N. And then this side will be the same thing but plus, right? So basically the key point here is, in this case, we know 40. We have 40 data points. That's a lot of data points. And because of that, it becomes normal. In this case, we knew the population standard deviation. In that case, we also use the normal distribution. Any questions? Okay. Okay. So a little bit of review. So if X bar is the sample mean of a random sample of size n from a normal population with known variance sigma squared, 100 times 1 minus alpha % confidence interval on mu is given by this equation, right? So here, since we know sigma squared, we use sigma here and we use Z, which means normal distribution. Now, if we have a large, basically, sample size, and we don't know the variance, right? So variance is unknown. Then X bar minus mu divided by S divided by square root of N is a normal distribution, right? Why is it normal? Because we have many samples, N is large, right? And since n is large, the central limit theorem kicks in. And the equation becomes exactly similar to the previous slide. The most important thing here is that we use z, and z is from the normal distribution, right? But here, since we don't know sigma, we use s instead of sigma, right? Otherwise, this equation is exactly the same as the previous slide, right? The only difference is that here we have s. In the previous slide, we had sigma. And s, if you remember what's the difference between s and sigma. So s is the standard deviation of our sample. Sigma is the standard deviation of the entire population. Okay. And then the final case that we considered was where we don't know variance. Variance is unknown. And we also don't have many samples, right? So n is 20 or 10 or 5. Right? So in this case, the equation is exactly the same as the previous slide. The only difference is that instead of z of alpha, we have to use the t distribution, right? So that's the only difference compared to the previous slide. Any questions? Okay. So let's move on. So now we covered everything we need to know about the mean, right? So we have a bunch of measurements, and we want to calculate the mean, like a mean of the population. We want to calculate confidence intervals for the mean of the population. Now, sometimes we are interested in the variance of the population, right? So variance of the population is a little bit more complicated, as you might have imagined. So basically, the problem setup is that we have n random samples from a normal distribution with mean mu and sigma and variance sigma squared, and s squared is the sample variance, right? Then the random variable x squared, which is n minus 1 times s squared divided by sigma squared, has a chi-squared distribution with n minus 1 degrees of freedom. Right? So this is how the chi distribution looks like. So so k here is the degree of freedom. If k is small, we see that it's asymmetric. Right? And it's actually always asymmetric. But when k becomes very large, so here number 9 is shown. But if we have a very large k, then it becomes symmetric, like a normal distribution, right? And the other important feature is that it's always positive, right? So it's never negative. And we will see why. It actually comes from the fact that variance is always positive, right? You never, when you calculate confidence interval for the variance, you can't say that, oh, it's between, minus 0.5 and 0.5, right? That doesn't make sense. Variance, the minimum value of variance is always 0. It never gets smaller than 0, right? And because of that, chi-squared distribution always starts from 0. It's not defined for negative numbers. And as basically k becomes large, it becomes like a normal distribution. Okay. So if s squared is the sample variance from a random sample of size n from a normal distribution with unknown variance, then a 100 times 1 minus alpha % confidence interval on sigma squared is given by this equation, right? So basically what we want to do now, note that previously we had like mu is between something and something else, right? Now we want to construct confidence intervals for sigma squared, right? So what's the confidence interval for the variance of the population, right? And all of these are known from the question, right? So we basically, in your project, for example, you have a bunch of data points, so you know n, you know s, you calculate s from your data points, and basically this value, chi-squared of alpha divided by 2 and n minus 1, this comes from a table. And this is another table provided in the formula sheet. one thing that is different, it looks very different compared to the previous equation. For mu, for example, the confidence interval was x bar minus something and x bar plus something, right? Here is not like that at all. Here we have, sigma squared is between s squared times something and s squared times something else, right? So here, like I drew an ellipse, and here I drew a rectangle because the things that are multiplied by s squared in these two cases are different, right? So one very important point is that for mean, the lower and upper bounds, both of them were, in all cases, for both z and t, were, for example, z of alpha divided by 2, right? So both of these were z of alpha divided by 2. In this case, it's chi-squared for the lower bound, is chi-squared of alpha divided by 2, but it's chi-squared of 1 minus alpha divided by 2, right? So that's a very key difference compared to the mean, compared to the confidence interval for the mean, right? So these are completely different than before, right? So don't worry if, nothing makes sense. We will do an example, and hopefully, this equation will start to make sense. And one basically final point is that, remember, this is confidence interval for the variance. If you want to calculate confidence interval for sigma, you have to calculate the square root of those, right? Okay. So similar for the mean, where we have upper and basically one-sided confidence intervals, we also have one-sided confidence intervals here. So in that case, for lower bound, it's chi-squared of alpha instead of alpha divided by 2. And for the upper bound, it's 1 minus alpha instead of alpha divided by 2. Sorry, instead of 1 minus alpha divided by 2. So if I go back to the previous slide, this is 1 minus alpha divided by 2. Here, it's simply 1 minus alpha. We don't divide by 2. Right? Okay. And again, it's important to note that these are different compared to the confidence intervals for the mean. For the mean, we always had, either t of, for example, alpha and n minus 1, or z of alpha and, sorry, there's no n minus 1 here, or z of alpha, right? But here, it's not, so both the upper bound and the lower bound had basically these. But in this case, the lower bound has alpha, but the upper bound has 1 minus alpha, right? This is different from the mean. And we will do an example right now, and hopefully it will make sense after the example. Right? So we have an automatic filling machine that's used to fill bottles with liquid detergent. A random sample of 20 bottles results in a sample variance of s squared equal to 0.015. Assume that the fill volume is approximately normal. Compute a 95% upper confidence interval, right? So the question says upper, and because of that, we are interested in this upper bound. Right? So from this equation, we have n. So n minus 1 will be 19. We have s squared, that's 0.0153. The only thing we have to calculate is this guy, right? Chi squared of 1 minus alpha and n minus 1, right? And the question says 95%, I guess. Yeah, 95%, right? So since it says 95%, that means that 1 minus alpha is 95. right? So we look at the table at 95 here, and then n minus 1 is 19. So the number that we get is down here, 10.12, right? So divided by 10.12. So that's it. That's the final answer. Yeah, sigma squared is less than that. Yeah. No. This is the chi-squared number. We don't need to square this guy. No. Yeah. Thank you. Yeah. So that was a good question. So this table gives us already chi-squared numbers, right? It's called chi-squared distribution, right? So you don't need to square this guy anymore. Right? So these are percentage points for chi-squared. If you look at the table, it says chi-squared. Right? Yeah. Thank you. So we basically know that, sigma squared is always less than, 19 times 0.0153 divided by 10.12 with probability of 95%, right? So that's what it means when we say that the 95% upper bound confidence interval is this, right? So for sure we know that sigma squared is less than this quantity with a probability of 95%. So what if the question wanted lower bound, right? So compute a 95% instead of upper bound. What if the question wanted lower bound confidence interval, right? So I should change the color. So lower bound confidence interval, right? So for lower bound, we have to use this other equation, right? Because this is the lower bound. And everything remains the same. The only difference is that now I have to use, so it will be still 19 times 0.0153 divided by, so instead of this number, 10.12, here is chi-squared of alpha and then minus 1. So alpha was 0.05, right? So from the table, I go look at 0.05 here. And the number that I get is 30. Right? Yeah.
So there's like, in the table there's like 5, 10, 25, 50. Like the other ones, like what you just interpolate between the
Yeah. I will answer that. That's a very good question. So here is 30.14, right? And if you look at this number, right, and contrast it with this other number, you see that this number is smaller, right? 3 times smaller, almost 3 times smaller, right? So it does make sense. So because here we are dividing by 30, and I just noticed that I can use this before to to highlight things. I used to draw under them, which made things very messy, but I just realized there's something here. So here is divided by 10, and here is divided by 30, right? So one of them is almost 3 times smaller. And the question, there was a very good question. What if we wanted, instead of like a 95% confidence interval, what if the question wants 98% confidence interval, right? So, we don't ask those questions in this course, but if we do ask, you can just look at the closest number. You don't need to interpolate, right? This course is not a numerical, recipe course, so you don't need to do but the proper way is to do bilinear interpolation. There's something called bilinear interpolation which is used for, when you want to interpolate in 2 dimensions. But in this case, if we want an 98% confidence interval, you can, look at the closest number that is provided in this table and report those instead. And by the way, that's also an interpolation method. It's called closest point interpolation. Okay. So yeah, it's the same answer that we just provided, right? Is it 20 minus? Yeah, 19 times this guy divided by 10. So there is a 95% chance that your sigma squared is smaller than this guy. Right? So if the question wanted, instead of upper bound, if the question wanted a lower bound, then we would use this equation, right? Which is what we just did. And if the question wanted, a two-sided confidence interval, we had to use this equation up here, right? This is the two-sided version. Any questions? Okay. So this table from the book provides a very good summary of, everything that we learned in chapter 8, right? So in my opinion, chapter 8 is not difficult. In fact, in my opinion, it's the easiest chapter. And if you look at the sample questions from the exams, there's always at least one question from this chapter, right? And these are usually, if you just understand the idea, these are easy questions to solve, right? So there is 4 cases in total. 3 of them are concerned with the mean, right? So 1, 2, 3, and one of them is concerned with the variance, right? So we want to calculate the confidence interval for the mean, and we know the standard deviation of the population. In that case, we use normal distribution, right? We want to calculate, again, the mean. We don't know variance, but we have a large sample size, right? Again, we use the normal distribution. Why we use the normal distribution? Because the central limit theory applies. And then the most complicated case is where we don't know standard deviation, and we also don't have many samples, right? We have like 20 samples or 10 samples. In this case, we have to use the t-distribution. And for the variance, we use chi-squared distribution, right? So that's the entire chapter 8, in my opinion. Any questions? Okay. So now we are ready to start chapter 9. But before we do that, there's a few, announcements about the project. So as I said in the first class, the due date is the last. So the due date, I'm not sure actually if these dates are correct. So I don't know when is the last day of the tutorial. I just asked the TAs and the TA coordinator to tell me, right? So I don't know. These dates might be incorrect. But basically, the due date is the last day of the tutorial, right? And, for some reason, we are seeing I did update the slides. I guess this is not synced. Yeah, okay. So yeah, this is not synced. So I'm not sure about these dates, right? Whatever, whenever the last day of the tutorial is, the due date is on that day. I don't recommend that you do a hard copy submission. I recommend that you do a soft copy submission. And again, this is incorrect. You shouldn't email it to him. He has already created a submission page on Moodle, right? So you should submit on Moodle. But this time is correct. So Tuesday, December 7 at 5 p.m. is, when you should submit your project through Moodle. Yes?
It's the last day of class is the 6th. So
Yeah, I know the last day of the class is on the 6th, but Yeah, so but the tutorials are on Tuesdays and Thursdays, right? And I don't know if there are tutorials on, after the last day of the class or not. Yeah, I did look at that. The last day of the class is Monday, December 6th. Yeah.
Are both the hard and the soft copy mandatory?
No, just one of them. Just one. And in fact, I recommend that you don't do hard copy, right? So I recommend that you just submit through Moodle. But I will ask, the coordinator to find out what is the last day of the tutorial if you want to submit, hard copy. And late submissions will not be accepted, and you should include your, your data points in your report, either as an appendix or, in your report. And basically, your project will be evaluated by 4 indicators: background and hypothesis, designing experiments, conducting experiments, and collection of data, and analysis and interpretation of the data, right? Okay. So the final chapter of the book is about hypothesis testing, right? So a statistical hypothesis is a statement about a parameter of one or more populations, right? So for example, we have a new engine, and we make a statement that the mean torque of this engine is this number, right? And we want to either reject that hypothesis or basically we usually want to reject the hypothesis, right? So and the reason for that is that like let's say from physics, or let's say we know that the previous model of this product had this mean, and we have designed a new model, and we want to show that the new model, for example, is better, right? So we have to prove that the mean, for example, torque of the new engine is more than whatever the mean torque of the previous engine was, right? So the statement, for example, our null hypothesis is that mean is 50 centimeter per second, right? We are looking at the velocity of something. And the alternative hypothesis is mean is not 50 centimeters per second, right? So this is called two-sided hypothesis testing, right? Two-sided meaning that in H1 we don't specify whether mean can be more than a number or less than a number, right? We just say it's not equal to, right? We also have one-sided hypothesis testing, where the null hypothesis is again equality. Always the null hypothesis says mean is equal to something, right? So mean is equal to 50, and the alternative hypothesis is mean is less than 50, right? So we want to see, which one of these hypotheses is correct. So as you can see, there are a lot of similarities with confidence interval. So this is like a one-sided confidence interval, and this is like a two-sided confidence interval, right? And we will see that the way we compute these is also quite similar. In fact, exactly the same as confidence interval, right? So this chapter is sort of like a repetition of previous chapter, but in different words. Okay. So where does the number 50 come from? It can come from past experience or knowledge about the process, or even previous tests. The objective of the hypothesis testing is then to determine whether the parameter has changed or not, right? Or it can come from some theory or some model regarding the process, right? So, for example, the system is so simple that we can actually write the physics laws for it and calculate, the voltage that we get at the end, right? And then the hypothesis testing is that with the experiments, we want to verify the theory, right? Or it comes from external considerations, such as engineering specs, like, for example, the steel in some, bridge must, have at least this much, strength. Or from contractual obligations, right? You're selling something and you basically specify that this thing has a mean of, 50 centimeter per second, mean velocity of 50 centimeter per second. Okay. So what is the test of the hypothesis is a procedure that leads to deciding whether the hypothesis is correct or not, right? So we will basically we will follow, several steps to prove whether a hypothesis is correct, or we say that, we don't know whether it's incorrect or not. Basically, we say that we fail to reject it, right? So the idea is that we have a random samples, we have a bunch of samples, and from these samples, we want to draw conclusions about the population, right? So for example, we have a very, very large population, right? And our null hypothesis is that H0 is that mu is equal to 50, for example, right? And we have a bunch of samples, right? And we calculate X bar from these samples and we get X bar of 49, right? Or we get the X bar of 49.5, right? So we want to say whether mu is actually 50, or we want to see whether this X bar gives us enough confidence to reject this null hypothesis. Right? Okay. So in order to do that, we have to basically calculate some boundaries, right? So this is the boundary, right? We will talk about how we actually calculate these boundaries, right? And if X bar, falls here or here, we say that we reject H1, right? So if X bar is, outside of this, original small region, we say that we reject H0. And if it happens to be, close to 50, the correct statement is that we fail to reject H0, right? We don't say that we approved H0, because this test is not about approving the null hypothesis, it's about rejecting the null hypothesis, right? And that's why, in fact, it's also called null, because it's something that we want to reject, right? For example, we have improved, the quality of our production or the design, so we want to show that, the new mu is actually, for example, higher than the previous mu. Okay, so this table is very, very important, right? So whenever, you feel lost in this chapter, I highly encourage you to refer to this table, right? This table is about two types of error that we are prone to when we do hypothesis testing, right? So we have two cases in total. Either H0 is true or H0 is false, right? So this is, like, let's say we have an oracle, and the oracle tells us that H0 is true or H0 is false, right? So that's the real truth, right? And let's say if H0 is true, but, so for example, assume that H0 is actually true and mu is actually 50, right? But we calculate X bar, and X bar happens to be 52, right? And the range that, we had specified before was a smaller range, right? In this case, we say that, 52 is outside of that range, so we reject the null hypothesis. But since H0 was true, we reject it, by mistake, right? That's called type 2 error. Right? And there's another type of error that's called type 1 error, which means that, actually, I think I made a mistake. Sorry about that. So what I said, I think, was correct. I don't remember what I said, so I will say from the beginning, right? So the first case, so forget about everything I said here, because honestly, I don't remember what I said, but I think I made a mistake. So assume that H0 is true, right? Meaning that the actual mu is 50, right? And this comes, from the oracle, right? It's unknown. But we know that H0 is true. So we are in this column, right? And say that somehow, the X bar that we calculate from the samples, we are very unlucky, right? And all of the X's that we sample are quite large, right? And at the end, the X bar that we get is 52. And, before that, we had specified a smaller range for rejecting the null hypothesis, right? So in this chapter, we will talk about how to find these bounds, right? These two numbers. So don't worry about how we find them for now. Let's assume that somehow we had a range, right? And assume that the X bar that we find is outside of that range. That means that we are rejecting, so since it's outside of the range, this means that we reject the null hypothesis, H0, right? But remember that we assumed that the null hypothesis is true, right? So we reject it in error, and that's called type 1 error, right? And that's denoted as alpha always. So alpha is probability of type 1 error, which means that probability of rejecting H0 when H0 is actually correct. And there is a second type of error. So assume that, again, our null hypothesis is that H0 is, mu is 50, right? So this is our null hypothesis. And assume that, our correct mu was, in fact, 52. So here I run out of parameters. So 52 is, correct. Right? So our null hypothesis says that mu is 50, but our correct mu is actually 52, meaning that our correct mu is actually not 50, right? So this means that the null hypothesis is false because the null hypothesis states that mu is 50, but our mu is actually 52, is a larger number, right? And let's say that by chance, right? So when the correct mu is 52, it means that our distribution is something like this, right? So let's say by chance, all of the samples that you collect are smaller than the mean, right? Let's say you only have 4 samples, and those 4 samples, all of them are smaller than the mean, and the final mean that you calculate is quite similar to 50. And that means that you cannot reject the null hypothesis, right? Even though the null hypothesis is false. So that's called type 2 error, and it's denoted with beta. Right? So that means beta means probability of failing to reject the null hypothesis when the null hypothesis is actually incorrect. Right? So don't worry if you didn't understand. We will talk about both. So the next this entire chapter is about type 1 and type 2 errors, right? So we keep calculating this, and I will keep plotting the distribution, so it will make more sense if you didn't understand. Right? Another, like maybe another case that you can look at this is, let's say somebody goes to a doctor with, a brain MRI scan, right? And the true diagnosis is either this person, has this condition or this person doesn't have this condition, right? A certain condition, right? And the doctor can also say that, oh, you have this condition or you don't have this condition, right? So you can see that it becomes a table of 2 by 2, exactly similar to this, right? Either has the condition or doesn't have the condition, and then the doctor's decision is either you have the condition or you don't have the condition, right? So maybe we can add that as a slide here. So I think that's a bit easier to grasp. So we will have a table quite similar to this case. So we will have a table. So this table will be, so at the top we will have true condition, right? So let's say we are looking at stroke, right? So has stroke. So the patient has a stroke or doesn't have a stroke. and this other basically the rows of the table. So these are the columns of the table, and rows of the table. First row is doctor diagnosis positive or doctor's diagnosis negative, right? So the doctor either says you have stroke or you didn't actually have stroke, right? So again, we will have 4 numbers exactly like before, right? And these are exactly the same. Basically, it's exactly the same concept. One of them in this case is called false positive, and the other one is called false negative, right? So you say it's positive, but you're incorrect. In the other case, you say it's negative, but you're incorrect, right? The concepts are quite similar. But this is not in this course, right? But I think it's easier to understand. Okay. Any questions? All right. So suppose that the standard deviation of the population is 2.5 and sample size is 10. And we want to calculate the probability of type 1 error. I think let's do this one. So it's, I think we covered enough material for today. Are there any questions? No? Yeah.
Can you go back to the doctor example?
Back to
The condition.
this one?
The one you
This one?
The doctor's,
Oh, doctor? Oh, yeah, sorry about that. Yeah, thank you. Yeah.
Can you write down which type of error is based?
Sure. Yeah, sure. Let's try to do that. So in this case, the true condition of the person is positive, and the true condition of this person is negative, right? So here, if the doctor's diagnosis is positive, and here is also positive, there's no error, right? And if the doctor's diagnosis is positive, but patient doesn't have a stroke, here this is called false positive. Oh, this is not called type 1 and type 2 error anymore. So these are different concepts, right? So this is called false positive. And this one is called false negative and no error. Right? So these are different compared to type 1 and type 2. They are related, but they are not the same thing, right? So in medicine, this is called false positive rate and false positive rate and false negative rate, right? But it's quite similar, right? But it's not called alpha and beta anymore. Yeah. Any other questions? Okay, so see you guys on Wednesday.